Hi guys, welcome to Learning Electronics Repair and part 2 of all you need to know about diode mode to fix stuff. If you watched part 1, and I hope you did, otherwise go and watch it, because why watch episode 2 without episode 1? In the first video we looked at diode mode, continuity and resistance mode. We had a look to see what was coming out of the meter, what voltage, what current, and worked out how these two modes work and what the difference is. And then we had a look at components out of circuit and the various problems you may find in testing them. In some ways they may fool you, so do watch that one right through to the end and I'm sure you will learn some things. But in this second part we're now going to look at testing in circuit. So get your coffee, your beer, whatever, settle down and maybe learn something new here as well. Okay, let's do it. Let's look then at some of the holes that are just waiting for you to fall in them. Okay, very common ones. Diodes that look short circuit in circuit when they're not. Most common reasons for this one, something like a relay coil, but it could just as well be a little switch mode power supply. Low value resistor, MOSFET, primary of the transformer. Okay, and across here, as I've mentioned before, you will see this diode to stop what's called back EMF, which is the high voltage generated here when this MOSFET switches off. That diode will look like it is short in circuit. The reason being because this coil is a very low resistance across the diode. So watch out for that type of scenario. The other one I've just drawn is very similar. A relay. Transistor switching the relay on or off. Ground, base, and from here to here for the same reason, a diode. Now because the relay coil has some resistance, usually at 100 ohms or something like that, could be less, this may not look like a short across the diode, but it'll look like it's conducting in both directions. It's not, it's the coil. Yeah, you can prove it by lifting one end and you'll test the diode, or take it out altogether and test the diode and find it's fine. So where you see inductor coils with diodes near to them, they can look like they're short when they're not, even though there's no fault condition. Very similar to that one is this, and again it's a diode with a coil near to it. Okay. I don't know why I've written plus V there, because this is just AC. This is your secondary of your transformer. Okay, this end is connected to ground. You have your rectifier diode. You have your electrolytic capacitor, maybe some inductors for smoothing. Then you have the load, whatever this power supply is driving. Now normally you can measure this diode in circuit and it just looks like a diode. It will conduct in this direction. Put your red lid here, your black lid here, you will see a diode junction. If it's a Schottky diode, you'll see a lower voltage diode junction, but you'll see a diode junction. Okay, and that's fine. The problem occurs when we have a short circuit here on the load. If you measure this diode, the diode will read short circuit. Why? Because from this end where 1 meter probe is and the other meter probe is here, we have a short through there, back through the winding, which is very low resistance to there. So that diode will read short even though there's nothing wrong with it. I mean, it may be short, but it may not be short. So if you have that sort of reading across a diode and you see a short on the output to ground, there's every chance the diode is possibly. We'll say, okay. So that's another one. Another good one which will fool you is power transistors. I can actually show you this. I have a good example of this. And you'll normally come across this in amplifier circuits in particular, but it could be any power transistor. So on an amplifier, a large power amplifier, audio amplifier, your output stage will consist of a number of large transistors in parallel. Each one will have a resistance. Effectively, this is where your speaker connects. This is your positive, and you'll have the same thing effectively upside down with a PNP here. This is your negative base, okay? You'll have that sort of circuit, and this goes speaker to ground, plus and minus drive. Now, these resistors, and we can only draw one, these are normally about 0.22 of an ohm, okay? That's the emitter resistors. The drive comes in here quite typically 22 ohms. Doesn't have to be, but these are good typical values. 22 ohms. And then you have a base emitter resistor, which is probably connected to here, but it could be connected to there. We'll connect it to there. And this resistor is 2.2 ohms, okay? Don't be surprised, I'll draw it the right way, don't be surprised to find low value base emitter resistors on a circuit like this. If you measure this transistor, which we're going to try at the moment, and you measure the base 2 collector, it will read fine, it will read like a diode junction. But when you read base emitter, you'll read a low resistance, not a short, but a very low resistance in both directions. And that is this resistor, this one. Let me show you. It's easier to show you and probably makes more sense than try to explain it. So here is a large power amplifier. These are output transistors. I think this one is the base. Let's have a look. You can see the emitter resistor, 0.5 ohms going to ground, okay? So if we measure base collector, yes, I've got it the right way around, we see like a diode junction, 0.388. That reads like a short, but it's not quite short. Look, it says 0.011. Go the other way. This now reads fairly much open, high, and this reads like a short, and you'll find that across all of these. Fairly high, short-ish, diode junction, like a short, okay? That doesn't mean these transistors are bad. Base emitter in this type of power circuit, you will usually find a low value base emitter resistor, okay? I can flick it over actually, we just have some transistors here. This side's disconnected. So, same sort of thing. Base collector reads like a diode, and notice you're reading less than 0.5. These are large power transistors, that's not unusual. Base emitter, they're fine. Yeah, 0.489, 0.462. Notice also with these, we can tell which is the emitter. Higher reading. And we don't have that low resistance. So, base emitter, power output stages, expect there to be a low value resistance there. While we have the circuit board here, let's have a quick look at it. So there are some more transistors. Let's see if we can identify them. So this one first, I don't know what it is, but that's reading fairly high. Okay. That reads like a diode junction. That reads like a diode junction. 0.594, 0.606. So NPN, because the positive lead is on the base, NPN, okay. Collector, emitter, good transistor. So look at this one. This is kind of back to front, let's see. That reads like a diode junction. That reads like a diode junction. Now, I've got the black on what looks like the base. 581602 base collector emitter. If we go the other way around, let's see what we get. So red on the base, you'd expect this to be open. Open. Well, it reads a high reading, but it's fairly open. How about between the collector and the emitter? Okay, 212, so it's quite high. A bit lower. Okay. Which not reading a diode junction. Obviously there are resistances in here. Try another one over this side. Let's have a look. Is this the same device? Well, that reads open. That reads pretty much open. Let's go the other way. Junction. Open. Junction. Junction. Okay, so this end is the positive. This must be NPN if it's a transistor. 598 611 base collector emitter NPN. So that's how we can measure some of these. Let's look on some surface mounted devices. Well, we have a few here. These are marked PQ, so we can pretty much say Q. They are either bipolar transistors or MOSFETs. Let's see if we can figure out what they are. So this one, this will be the base or the gate. Nothing there. Nothing there. So this is the red lead. It's not an NPN transistor. Let's go the other way. Nothing there. Nothing there. So it's not a transistor or it's faulty. If it's a MOSFET, we should see the parasitic diode between the other two. There's a diode junction there. And there isn't one there. So we can say that's a MOSFET. Without the pin out, we can't say if it's N channel or P channel because we need to know which is the drain or source. But we can say it's a MOSFET. Now you'll probably see that we can't switch this on in circuit like I was doing with them out of circuit. And that's because there is a resistance from here to ground that drains the charge. It won't let me charge the gate up. Okay. From here. Here. Try and charge it. See, it won't switch on. I'd have to take it out of circuit. So with a device like that, if I'm probing around, I can say it looks like a MOSFET. If I knew the drain and source, I could say P channel or N channel. To really test it, I would have to take it out of circuit, but it ain't short and it ain't open. So the chances are 90% or so. That is a good MOSFET. So look at the next one. What's this thing read? So again, base or gate. What have we got? Nothing. Nothing. Go the other way around. Nothing. Nothing. Again, does it read a parasitic diode? Yes. Other way should read open, you would think. Haven't lost it. It's there. Okay. Reads open. So that reads like another MOSFET. Don't worry about his high readings I'm seeing here. Obviously, the sort of stuff in circuit. Does this one read the same? Go into the pin. Open. Nothing there. Now that reads like a junction with a black lead to here. Does this read the same? No. Okay. So this one reads a little bit strange, it would seem, because that would be the base or the gate. We don't have a junction there. We don't have a junction there. Switch around. We do have a junction there. and we do have a junction there. But I wouldn't be worried about this sort of thing if I found this myself, and I'll show you why. These two devices are both the same. KP. KP. Without looking up the data sheet, we can compare the two. Now, I'll put the red lead on here. Nothing. Same with this one. Nothing. Red lead on here. 0.593. This one, 0.591. Almost the same. This is almost certainly a parasitic diode, okay? On this one, from here to here, is open. And this one, I see a diode junction, okay? Now, we can also go from here to here. There's nothing. So there's no short between those two pins on this one. I can think of no failure mode that would cause that component to fail in that way. It just seems to be the same as this one, the only difference being that this has a diode somewhere here, quite possibly inside this chip, which is effectively between there and there. And we'll probably also find, if this is the gate or the base, and this is probably going to be a gate because this looks like a MOSFET. If I put the red lead here, positive, to there, I see the diode junction. And I suspect this is probably the source. That's just a suspicion. But I can go a bit more than suspicion, and I'll show you what I can do. So I can say, okay, is this pin connecting to ground, the metalwork? Yes, it is. So I know straight away that I put a positive lead, my red lead, on here to here, and I see that diode junction. That polarity will not occur during normal operation because this board has a positive supply. So the ground can never be positive with respect to this gate. So that diode that we see will never conduct, not in the operation of this circuit. So when you find something like that, that's a perfect example of checking the polarity, seeing if one end of these is ground or as a power rail, and from that working out whether that junction you see is something that can ever occur in normal operation of the circuit. And you'll find the same thing with bipolar transistors, where there appears to be, you found the base collector, base emitter, you can tell the voltage, one being slightly more than the other, which is emitter, which is base. But when you then go collector emitter, you find a diode. In that case, you know which is the base, you know which is the emitter, you know which is the collector, you know if it's NPN or PNP because of polarity of your lead. So you can say this is an NPN transistor or this is a PNP transistor. And then because you know that on an NPN the collector is a higher voltage than the emitter, you'll know whether that diode you see across collector emitter is reverse biased in normal operation. If it's reverse biased, don't worry about it. If it's forward biased, you need to find out why. And I'll just put that on a piece of paper as well, just to make it a bit clearer. Yes, this is always easier when you draw it. So you'll sometimes find this. Transistor you're measuring. You put your red lead on here and you see a diode junction both ways, and this one is slightly higher than the other. As we've seen, maybe this one reads like 5.548 and this reads like 0.551. So you know it's the emitter, you know it's the base, and because this is the red lead, you know it's NPN. You should then expect collector emitter to read open both ways. But when it's in circuit, what you may well find is you read in this direction or the other one a diode. If you see that diode, you've got to think, okay, could this be a fault? And the way I do it is I say, okay, this is NPN. This end will always be positive with respect to the emitter. It has to be. It's an NPN transistor. This diode is reverse biased in this direction. Therefore, in normal operation, it doesn't exist. It's not a problem. If I find the same thing like this, and you know it's just the opposite of what I've drawn, and I find what effectively looks like a diode going that way, yeah, collector emitter, and it's NPN. This end must be positive with respect to this end. Why am I seeing a diode junction here? Because effectively that means that the voltage on here cannot be more than 0.5 volts or 0.15 for Schottky than the voltage on that end, and that is not normal. Okay, so when you see these strange diodes, put the voltage on so you know which your base emitter. When you see these strange diode junctions, think about it that way. Yeah, you don't need to know where the power rails are. If it's a PNP transistor, you'll know because your black lead is on here when it's conducting, you know it's PNP, and you'll know that the collector on the PNP is going to be negative with respect to the emitter. So the diode junction, if it's something you don't need to worry about, will be the opposite way around. Okay? I hope that taught you something. That's one of them kind of like moments where the light bulb turns on in your head when you see and understand that. Okay? This is okay, this is not okay. Now you'll see I have two multimeters, and that's because we can do some clever tricks with two multimeters, both in diode mode. I've connected the black leads together, so I have one black probe connecting to the negative on both meters. This is the positive from the aneng, and this is the positive from my fluke. Now, if we have a look at a MOSFET again, we were looking at some before, there's one here. So you can see that this one, that reads open. That reads open. If we go to here, we see a parasitic diode. So this is a MOSFET. And we can test the MOSFET. And to do that, you need three hands, but I haven't evolved the third one just yet. So it is just about possible to do it with two hands. So what we do is we connect our aneng meter across the drain source. And we get the wire out of the way so you can see what I'm doing, okay? So if I can get it just in position, I can connect the aneng across there. Now I can use the diode mode to put a voltage on the gate. Watch. See? Look at the aneng, it's turned on, yeah? I'm not seeing a reading on the fluke because the gate is effectively open circuit. It's got a bit of a high resistance. And I think I'll probably just slipped a bit. Let's get back onto it. Yeah, there. Okay. So you can see I can turn that MOSFET on. I can test it. And I can do the same thing with bipolar transistors as well. This is a bipolar transistor. I can go onto the base, onto the emitter. I have a diode junction on the fluke. Collector, have a diode junction on the fluke. Let's connect the aneng collector emitter with the positive to the collector. Okay, again, we really want three hands, but we'll manage. So I'm now connected across the transistor. Now I'll come onto the base with this one. Look, you see a diode junction now, base emitter, and you can see that the transistor is switched on if you look at the aneng. Okay. So when I said that you can only test these things out of circuit, I wasn't being quite honest there. I wouldn't say I was being dishonest, it just wasn't quite telling the whole story. So you see, you can test transistors in circuit using two meters, both in diode mode, and that's a really useful thing to know when it comes to fault finding. Now, I won't say this will work all the time. If there is a low enough value resistor from the base to the emitter or from the gate to the source on a MOSFET, you may not get enough voltage in from here to turn the transistor on. But you can always check for that. You can think, okay, it's not turning on. Measure base emitter for in resistance mode, or measure to ground from base or gate in the resistance mode, and you'll soon know if you have a low value resistor there. On the same basis that, we can do a few other clever tricks as well. Probably too many to show you in this video, and I'm sure some of you guys are going to come up with a few more suggestions. But another very useful one I will show you. And these are opto isolators. Now, with the opto isolator, one side is the LED, and we should be able to see it on the fluke. Okay, is it this one? No, is it the other way around? Yes. 0.9. Remember, an infrared LED was about 1 volt. If you saw part 1, you'll know that. If you didn't, well, you should have done. Okay, so what you can do is, and this, it needs even more hands, as you can clip some wires onto here. That's probably the easiest way to do it, unless we're lucky and both grounds are connected together. But they shouldn't be, because it's an opto isolator. So actually, in fact, that wouldn't be so lucky. So I'll just put some wires on here. Okay, we're ready. So I've clipped these on. These are going to the aneng. So this one's actually going to the red lead on the aneng, and this is the black lead. And at the moment, this is in resistance range. This one is in diode mode. Now, I have separate red and black wires now on the fluke. They're not connected, the two blacks together. Because this is an opto isolator, it isolates, so the ground on this side of the circuit is independent of the ground on that side. That's what it's supposed to do. Yeah. So watch what happens now if I use diode mode to turn the LED on. Well, you can see 9.2, 9.3, that's the diode, and you can see the resistance is lower on the aneng. You may do this in diode mode as well. It depends a little bit on the opto isolator. Let's see. In this case, it didn't actually do it. I can only assume that's because it's not turning the transistor fully on. It's not on enough to actually conduct, but it's on enough to read a lower resistance. Okay, we'll go back into ohms range again. Let's go for it. And there you go. So you can see we can switch the opto isolator on and we get a very good indication that it's working. So that's another thing you can do with 2 meters. This time one in diode mode to switch the opto isolator on, and the other one in resistance mode to measure this transistor. What this test relies on is the fact this is your positive supply and this is your negative supply. So on a single supply rail, plus volts and ground. On a dual supply rail, plus volts, minus volts. But this end is negative compared to that end, the rails. Inside here, there will be protection diodes normally connected in a reverse biased direction. So with effectively, if you like, the cathode here, I can even sort of scrape it onto the chip, and the anode down to here. And you'll find that on all the inputs and possibly on outputs as well. So normally they're reverse biased. They're just there to effectively guard against reverse voltages. So what we can do is put the positive lead onto the negative supply rail or ground. Now let's have a look at what we see. So normally on a dual op amp, this is one of the outputs, and these pins 2 and 3 are inputs, inverting and non-inverting, whichever way around they are. I think this is normally the non-inverting, but I'd have to look it up, and I'm not going to do. The same with this one. This is the output, and this is non-inverting and inverting. So let's see what readings we get. So we'll go to here, and that's reading 0.56. Expect to see a diode junction. And to here, okay, a diode junction, a different reading. And to here, this is the output, a diode junction, okay. Now let's look on the other one. So input 608, input 624, output. So they're all reading about the same. This one, these two, this one reads a bit lower. Okay, but I wouldn't be worried about that. If it reads short or open, I think I have a problem. Certainly enough to remove the chip and test it. Here's another chip of the same sort. Let's go again and see if it reads basically the same. So 559, 624, slightly higher. 640. So again, this one reads a bit lower like it did on that one. We should be able to read from here because this ground supply will be the same as that one. Yeah. On the other side, 608, 624 output. And they read about the same as each other. We've got a third one. And if these are reading like this, almost certainly there's no severe problem. Again, that one reads a bit lower. 624. Down to it. 640. 608. 624. 642. So they read like each other. If you find that, it's extremely likely they're all okay. That's a quick and dirty way to test op amps. Okay. These chips, I don't know what they are. I suspect they're probably op amps as well. So let's try the same thing. Positive to here. 470. 602. 607. So again, this one lower. Okay. These two, 470 again, 615, 651. So I suspect that is okay. Here's another chip of the same sort as that one. Okay, 469, 603. So again, this pin reads a bit lower than the others, and then on the other side, reads a bit lower. Okay. Okay. What you're looking for here is drastic differences or shorts. Which I guess is a drastic difference. Shorts and open. So that's a quick and nasty way to test op amps, but it'll probably get you by in well over 90% of cases. Let's look at a few logic chips. So these are 74HC32. These are quad OR gates. They sort of go in, out, ground, in and out, power. And we're going to do the same trick. So we're going to put the red lead onto the ground pin, okay? And we're going to see what we get. So I expect the two ins to read the same. .663, 663, and this is the out. Reads slightly different, 630. Second gate, 663, 663, 630. Up the other side, that's an out, 629, 663, 663. Okay, this is the other out, 630, 663, 663. So we can't say what the readings will be for any given chip, but we can say if all the gates in there are the same, or if inputs read the same as each other, if it's just one gate. So that's a way to test logic chips, the same quick and nasty way. Remember, when you do this, to put the red lead onto the ground, you reverse the normal polarity. And we can do the same with CMOS chips as well. So this is a hex inverter chip, in, out, in, out, in, out. Same up the other side, or something like that. Let's have a look at it. So red to the ground pin. Let's see what we get. Diode 656, 622, 656, 621. 655, 621. I'm not sure what this pin is. It's something different, an enable or something. 555. Then the same up the other side. 655, 62 something. Yeah. 6556, 62. And that reads open. 656, 621. So we can see on this one that this pin, which is 9, 10, 11, 12, pin 13 reads open. Is that normal? Would we expect that? Let's look at the datasheet for 4050. Well, we can see from the datasheet that pin 13 has no connection. Okay, that's the one that read differently. Pin 16 also has no connection. I actually thought that was a power, but it isn't. So the fact that one is reading open and these are giving like 2 different readings for in and out, this chip looks okay, and that's the way you can test logic chips. Just take the data sheet, look at the pins, and just try to figure out if anything looks really out of place. There's one other situation I can think of where you could use your diode mode. So the other use, and you have to be a bit careful with this, but I'll explain it to you. If you have, for example, some sort of chip, maybe a buck converter or something like that, ground, and it has a feedback pin here and it has an enable pin here, and this is active high, okay, and this is supplying something like so, ground. If you find something like this and there's no output coming from it and it's not enabled, so the enable is low, depending on the resistances, what you can do is put your red lead on here with the device powered up. Okay, it's powered up. Black lead to ground, red lead to here. And what you're doing is you're putting about 3 volts in diode mode onto the enable pin, and you can switch that chip on. Okay, you can switch that chip on and see if it runs. So that's another possibility. This is for faults where, for example, there may be some pull-up resistor here up to the 3.3 volt supply or something like that, and it's floating and you're not getting the pull-up, and this is just floating, it's not switching on. So that is something else you can try, and it doesn't really matter if you try this with some chip that runs on a lower voltage than 3.3, because this is a constant current source. So when you stick it onto the enable, if this thing's running on like 1.05 volt logic, the enable's 105. When you stick your meter on there, you won't get 3 volts, you'll get 1.05 because it's a constant current source. So that is another use for diode mode, where you can actually use your meter in diode mode to enable a chip. Let's have a look at situations where we shouldn't use diode mode. We should use resistance mode, or at least it's better to use resistance mode. Okay, so the situations this normally occurs in is things like laptop motherboards, desktop motherboards, graphics cards, and these sort of things, where you have a lot of buck converters. You can recognize them because you'll see these coils. Sometimes they look slightly different to this, but you'll see coils on the board. We can have another board. This is a graphics card, so there's another one here, a small one, a larger one, these that look different, some more here, and sometimes they will look like this too. So in these sorts of circuits, you need to use resistance mode, and I'll show you why. The way the buck converter works is like this, although in actual fact this is a synchronous converter, but a lot of people call them buck converters, so hey, why not? We have a supply, usually 12 volts on these sort of boards, could be a 5 volt supply, which comes down to 2 MOSFETs. 2 N-channel MOSFETs connected in series, and the other end goes to ground, sometimes with a low value resistor here to monitor the current, but if so, it's a very low value resistor, so that's not really relevant to this. We have the gate of the 2 MOSFETs switched by the controller pulse width modulation. And then from the junction of the 2, we have a coil, That's those coils we were just looking at. They look various types, but they're all inductor coils, and they're all very low value in these circuits. Maybe less than a microhenry, they're small value coils, which means that they have a very, very low DC resistance. To your multimeter, they read like a short. On the output of here, we will have some capacitors, one or more, either normal capacitors or electrolytic capacitors, or both. And then we will have the load. Now the load could be CPU, GPU, RAM, various other things. And you'll find the same sort of setup in things like Android set-top boxes, many things these days. A lot of electronics. And this is also connected CPU to ground. The problem is that the resistance of this load in modern electronics can be very low. It can be 10, 20 ohms, but it could easily just be something like 4 ohms or 2 ohms or 1 ohm or 0.6 ohms. Even lower than that on like the latest GPUs, it could be like 0.3 ohms. So you effectively have, as far as your meter is concerned, what looks like a short here. It's not a short, it's just a load that has a very, very low resistance naturally. Now, if you use diode mode and you want to check these MOSFETs, this one, or if you like from here to ground, it's the same thing. Look, ground is there. This will read often like a short. And you think you've got a short circuit on this voltage rail. You haven't. You've just got a very low resistance load. But unless you use resistance mode, and on some later GPUs even a micro ohm meter, you cannot see that it looks like a short in diode mode. Let me show you a few examples. Here is an old laptop board. This had a processor in a socket. It's not a modern one, but it has an onboard GPU here, NVIDIA. It has a Northbridge or PCH here. And these will be powered from these various inductor coils. This one, these, and so on. More of them here. Now, if we go to diode mode and we look around this board, let's see what we find. So I'm going to measure to ground. I'll just go on the end of the VGA connector and let's look at some of these coils. So that reads like a diode junction. Yeah, fairly high, higher than a diode junction. So does that one. That looks a bit like a Schottky diode. That reads short. Well, it says 0.013, but it's bleeping like a short, yeah. This one, even lower, 0.002. That definitely looks like a short. Okay. We have a few more over here. That reads like a diode junction. That reads high. That reads like high, yeah. But they look like there's some shorts on here, but let's have a look. Let's go to ohms range and take the same measurement. So this one is high, 8.2 mega ohms. The same. This is the one that read quite low. It's 160 ohms. Yeah. What did this tell us? Like a Schottky diode, it's 160 ohms. This one, 19 ohms. Okay, so that's not a short, that's a resistance of a load. Diode mode looks like a short, and we had one over here even lower. In fact, no, it was up here even lower. This one. This is probably powering this GPU, by the way. Looks very much like a short. Let's go to resistance. No, it's not a short, it's a 4.3 ohms. That's fine for a GPU. So that's why you shouldn't use diode mode whenever you're measuring off these inductor coils. Always use resistance mode, because if you don't, you'll think they've got shorts where you haven't. Here's a GPU, GTX 1080, faulty one. We've looked at it before. I can't remember if the GPU was short or not, but it has some inductor coils on. Let's try these. So diode mode. Reads like a short. Yeah, or close to it. And it bleeps like a short. Yeah, it bleeps like a short. Those become like diodes, junctions. These ones will look like a short. Absolute short, dead short, yeah. This one's a little bit higher. A little bit higher. Dead short. So 1, 2, 3, 4, 5, 6, 7, 8. These are all in parallel. These are multiple phases on one voltage regulator module, okay? These are different ones. Let's look at those shorts in resistance mode. So this read very low. No, it's 58 ohms. It's fine, yeah. That's high. Little one here, we didn't measure this one. These are the ones that look like a short. Well, actually it's half an ohm. Now for a GPU like this is actually reading 0.3 shorted. For a GPU like this, 0.6, so it's about 0.2 the load. That is not a short when you're talking about high-end GPUs like this one. Okay, 1080 Ti. This you can clearly see it's high. They read high anyway. These read not as low as these. Let's have a look. 100 ohms. Almost certainly that's the RAM supply, but it ain't a short. Yeah, similar. Go back to diode mode. You think you've got a short, yeah? Or it is there. These are just reading short. So you can see that in this situation, use resistance mode. You'll just make life difficult for yourself if you do it in diode mode. Eventually you'll learn, but I've told you now, yeah, you know what to use. Well, I did start the video, the two of them, by saying all you need to know about diode mode and resistance mode to fix stuff. And I'll put my hands up and say, that's most of what I know, but there are other situations, and there always are going to be other situations. But I'm hoping that this video has given you some very good ideas to think about when you are testing circuits to determine if you have a fault or not. I'm sure you guys commenting will add to this little repertoire, and we probably will end up with all you need to know to fix stuff. I hope you enjoyed that one, and I look forward to seeing you all soon on another Learning Electronics Repair video. Ciao for now, guys.